This is mod psi xt squared dx. In principle, the result should be some function of t, right? Then if t equal to 1, then at some value of t, maybe you did this. What happens when t is not that particular time, but future? How do we guarantee that this will remain 1? Schrodinger's equation continued. It is the equation from which we get the wave function. We were introduced to wave function before that through what? The voice wave, right? That is our wave function that gives us the probability density, Wave function is everything in quantum mechanics. Every information, every physical information that we can get about the system, it is the wave function. The first thing you have to get, from which you can extract everything, and we will see. This is the only thing. So the wave function, first we saw that, okay, the voice wave is the wave function. But then we didn't know how to get the wave function. We know that, okay, wave function is everything, but how to get the wave function of a system? For example, a harmonic oscillator. What is the wave function? A particle in a harmonic motion, okay? Let's say it's a tiny spring. Atomic scale spring, let's say, nanometer length. This is very small something, molecule, right? You can think of this as just two molecules connected through spring. This spring is nothing but the electrostatic force between the two, okay? So this is vibrating. So this is a system, microscopic system of harmonic oscillator. So obviously this is governed by quantum mechanics. And so we have to start with some wave function that describes this particle, right? How do we get this wave function? That's where Schrodinger's equation comes. You have to know the potential function of the harmonic oscillator, or any other problem. It will be different for different systems. Then this equation, when you put the V there, solve this equation and find a psi xt. That's your wave function, okay? And we found some conditions on this, that our interpretation of wave function, if we take mod psi x squared, xt squared, it gives us probability density. So times dx is the probability. And if this is a probability, then it must satisfy what? This condition. Right? Total probability has to be 1. Okay. Let me explicitly write it. And we talked about how the function should die very fast. So psi x at plus minus infinity, when t goes to plus minus infinity, this must go to 0. And it should go to 0 very fast, right? Such that this mod psi square go faster than 1 over x. Then only we'll get what? Something like this, right? But the question is, Look at this. This is mod chi xt square dx, which means it will be integrating over x, but not t. So in principle, the result should be some function of t, right? This t is not integrated out. Only x is the integration. T will remain. And if this is so, then ft equal to 1 basically, right? Then at some value of t, maybe you did this, and ft is 1. What happens when t is not that particular time, but future? How do we guarantee that this will remain 1? Okay? So this condition is called a normalization condition. Okay? What happens is, you solve the Schrodinger equation, and you find some function. Arbitrary, right? I can multiply this by any constant, and this will be a solution again. Because this is some constant. Usually it's a complex number, complex constant. A1 plus A2, I, both constants. A constant like this. I can do that, and it will still satisfy Schrodinger's equation, because it's a differential equation. Then I can apply the condition on A such that this mod square dx is 1. So in the end, it will be mod A square equal to this 1. So mod A equal to square root of this whole thing, right? And we'll find the A, and we'll put the A there. Usually it will be mod A square, right? So you take square root, it will be mod A, but not A, right? A will be what? Some e to the power alpha, I alpha, right? It's some constant alpha. If you take mod, this will go away. E to the power I alpha mod of this is what? Just 1. Right? Because e to the power I alpha mod is what? Mod is this times this, like star, and then square root. So this is just what? 1. So in general, if I take away the mod, this should be the 1. But turns out this is just a constant factor to be multiplied. It does not change physics, so you can just plain ignore it. Then A becomes this thing. We are saying that this integral is a function of t, and what happens when t changes? This may change, right? The value of A might change. How do we solve this? We have to check that this integral indeed does not change with time, and then we are done. So what we have to do is we have to take a time derivative of this integral and show that it's equal to 0. So let's calculate that first. Okay, so this I can write as this is a derivative on time. So this thing, look inside, it's a function of x and t, right? But outside, look at this, x has been integrated out, so it is just a function of t. So a normal derivative is okay, because there is only one function of time. But when we take it inside, then we have to write del 3, because we have not integrated out yet. And so when it goes inside, there is x and t. Psi is a function of x and t. So we have to take partial derivative if we want to only change the time. Alright, so let's first calculate this thing. So mod chi square is what? Chi star. Right? Complex, this and the complex conjugate of this. That's mod chi square. For any complex number, you know. Mod j square is what? Z star. If you take derivative of this, what do we get? Chi del chi star del t plus del chi del t chi star. Right? This is what we get. Let's save this as some equation number 1. Let me write down once again the Schrodinger's equation. V chi equal to 0. That is our Schrodinger's equation. Alright, let's do. The aim is that this wave function obviously satisfies Schrodinger's equation. We are getting this chi from Schrodinger's equation. So the problem is that this is that, and then the aim is that when we integrate, we must get 0, right? ddt of that integral of mod chi square must be 0. That's our aim. We started like that. And so next, how can we proceed? The proof is that if this chi is a solution of Schrodinger's equation, if it is a real wave function that satisfies Schrodinger equation, then the derivative will be 0, not some arbitrary random chi, okay? And so we have to use Schrodinger's equation, right? So look at this. This one we don't know, but at least del chi del t, we can get it from here, right? We can get it from there, okay. And so how can we get del chi star del t? We can just take a complex conjugate of this equation. So first of all, chi star times del chi del t. So let's take a chi star product on this equation, right? Just like this, from this side. So what do we get? IH cross del chi del t, and then we multiply this with the chi star here. So chi star equal to h cross square by 2m del square chi del x square, and what? Chi star here plus v chi star here equal to 0. Fine. Let's call this 2a. Okay, now we need this one. This we can get by directly taking complex conjugate of Schrodinger's equation itself. So if you take complex conjugate, I will become minus I, right? So minus I h cross, and this del chi star over del t, fine, equal to minus, there is no I, so h cross square over 2m del square chi star del x square plus v chi star. Okay? Oh, all right. Now, once again, we have this thing. We need to multiply by a chi from this side. From this side. So let's do that. So we will have I h cross chi del chi star del t equal to minus h cross square over 2m chi del square chi star del x square plus v chi star equal to 0, right? Let's call that 2b. Now I have to write this thing somewhere else anyway, let me erase other things that we don't need. So this, let me write down this there. So minus IH cross chi del chi star del t equal to minus h cross square over 2m. What do we have? Chi del square chi star del x square plus v chi star equal to 0, 2b, and erase these things. Okay, these are the two equations we got. using Schrodinger's equation easily, right? Okay, what do we need? We need this plus this. So this is here, this plus this. What do we have to do? We have to take this minus this, right? Then IH cross minus minus plus, and we can get this thing. So let's do that. 2A minus 2B, and we'll get IH cross this plus this, del psi star del T plus del psi del T psi star. This side done. On the other side, this minus this. Okay, so let's take this minus this, so this becomes plus h square over 2m, so that del square psi star del x square minus this thing, del square psi del x square, and then there is a psi star. What happens to these two? They get cancelled out. Psi, this is basically mod psi square. V mod psi square, V mod psi square. They get cancelled out. Yeah, we need this, so let's take IH cross on the other side. So that becomes I on the other side becomes minus I. 1 over I is minus I. And 1H cross goes away. So we have this. Therefore, we can replace this thing using this right hand side here. So I cross over 2m. We have psi del square psi star del x square minus del square psi del x square psi star. Let's call that equation number 3. By the way, you have to repeat these calculations. Okay, only then you will be good at it. This is good. What we want is integration of this in the end, right? Dx. We want to make that 0 somewhere. So how can we get 0? 2 ways. One is when, like, some cancellation happens and then things becomes 0, right? Like you put integration, somehow this and this will be equal and they cancel out. But looking at it, no, they're not equal. One is psi, other is del square of psi star. Then this is del square of psi and then psi star. Not exactly equal to, they don't cancel out, right? So probably they will not. The other strategy is that, another thing we can use, if we can get psi somehow integrating out, psi or psi star as a result, like something like this, minus infinity to plus infinity, but the integration is over minus infinity to plus infinity. If we can get something like this, then we can put this equal to 0. Because remember the condition, that wave function psi goes to 0 at infinity, plus minus infinity. This was a condition. So we can use that condition and say that this is 0. So we have to go in that direction. And in order to get a psi out of an integration, if we can get like dx, let's say del x, and some psi here, right? Then this integration is just psi, the result. So we have to get a single derivative somehow. Just always while deriving, think about like what I want and then go in that direction. Otherwise, it will take time and then you will be going in many directions. So here we have double derivative. We can convert that into single derivative through usual differentiations by part. So I'm saying that I can do this. Psi del psi star del x minus del psi del x psi star. I'm saying that this is equal to this. just look at this. What is extra? So if I take derivative of this thing, what will it be? Psi del square psi star del x square. So this part is okay. But then there will be another part, del psi del x. So let's write it. First term will be like this. Yes, del psi, this, right? From this. The next term will be del psi del x, del psi star del x. Right? Then for this again, we'll have del square psi del x squared psi star, and then similar term, del psi del x, del psi star del x. You'll see that these two get cancelled out, and we get exactly this thing, del psi del square star, del psi star del x square minus del square psi del x square psi star. So this is really equal to that. So I can just substitute this here as my del x of psi del psi star del x minus del psi del x psi star. Now what is this? A total differentiation of something. And you know in integration that if you have a total differentiation of something in integration, then the result is just integration and the dx goes away, and you have this piece as your result of integration, right? Because it will become like this, some df, which we know to be f, right? Okay, so I mean this thing finally goes inside. Remember how you got here. It was a ddt of minus infinity to plus infinity dx mod psi square, right? From there to you got dx minus infinity plus infinity del t of this thing mod psi square, and this is equal to that minus I h cross over 2m integration minus infinity to plus infinity dx. Then you have del x of this thing, right? Okay, and then dx times del x. So this whole thing is basically d of this thing. So integrating out, you have just this thing from x equal to minus infinity to plus infinity. So let me write it down. So what you have is psi del psi star del x minus del psi del x psi star, then minus infinity to plus infinity. But then even if you put infinity here, so it's psi of x going to infinity. We said that at x going to plus infinity or minus infinity, wave function must go to 0. Otherwise your integral will be infinite. This is just the condition that we begin with. Probability 1 hor karone. And if that has to be done, amar psi fast এনেকুৱা হৈ যাব লাগিব, যি হোক কিন্তু লাষ্টত ইনফিনিটিত গৈ 0 হ'ব লাগিব, এইপিনে মাইনাছ ইনফিনিটিত 0 হ'ব লাগিব, নহ'লে এই এৰিয়া আণ্ডাৰ দিছ কাৰ্ভ কেনেকুৱা ফাইনাইট হ'ব, ৰাইট? চ' psi 0 হৈ যায় at plus minus infinity. That means this at this value also 0, this at this value also 0. Similarly psi star, it's just a complex conjugate, right? So both this thing, these we don't know, but at least this and that all are 0 by our condition. So if that is so, this whole thing becomes 0. And so we prove that this integration dx mod psi square does not change with time. It's a constant in time. And therefore, if you set this to 1 at one point in time, it remains 1 forever. That's the proof, okay? So if you take a wave function, you have some potential V, and you solve Schrodinger's equation, solve this equation. If you solve this, then whatever psi you get, you have to first take a logical one. Like psi cannot be 0. And the psi has to be 0 at x equal to plus minus infinity. It has to be 0. And if this is a solution of this, it will always maintain the condition that if you set this once equal to 1, it will remain like this. So you don't have to worry about later times. Once you have, let's say you have solved it, and you have some x and psi x and t. You solved Schrodinger's equation, and you got this, right? It's some function. And you know that this becomes a probability density times dx is the probability, right? And if you have a probability density, you know how to calculate expectation values. From your thermodynamics, I have taught you that any quantity A, its expectation value will be what? It's dx probability density A. Okay? Let's call this some function, let's say f. So this is what probability density f, of course divided by again, dx mod psi square, but we just set this equal to 1. So the denominator is 1. Once you normalize, you don't have to always do the denominator dx mod psi square, because this you calculated it already and set it to 1 by choosing a constant in front, so you don't have to worry about it. We'll do a small exercise, then you will really know what we mean. But what I'm saying is, expectation value of anything is given by this. If you remember from thermodynamics, if you have a probability density, that's it. Okay. So, if it is a position, so once again, if you had boxes, particles inside them, and each one had a wave function psi, okay? You just set the condition, what is the potential for a box, and set it in the Schrodinger's equation, solve the Schrodinger equation, find the psi, and that's the psi for all the boxes. Now you go and perform experiments on each box, and you find some positions, right? Then you calculate the average of the position. So what was the average position found? That will be close to this value. This is a theoretical value, okay? It's called the expectation value. This is what you should get. But if you take only 5 boxes, your average will be quite different from this. If you take 5,000, 5 lakhs, then your average, experimental average, will be closer and closer and closer to this expectation value. Just like tossing a coin, okay? If you toss 10 times, you might get 6 times heads and 4 times tails. But if you keep tossing 1,000,000 times, you will see that almost 50% now it's heads, almost 50% tails. And when you reach infinity, it's exactly 50% heads, exactly 50% tails. Similarly, if you had infinite number of such boxes, and you performed the experiment and took the average of the x, the position you found in your experiment, this will be. So, this is the expectation value of x. What happens when we take a derivative of this expectation value? So, this is the expectation value of position. We know what happens. We know what is the ddt of this. If you remember, it was IH cross by 2m dx psi star del psi del x minus del psi del x psi star. Okay. minus infinity to plus infinity, right? Here we have an x. So now del x of this we found, right? Remember? And then we integrated del x. But now we have an x multiplied here because of the x expectation value. Once again we can use the trick. So this is what, this is some whatever f, and this is x. So what we have is dx del f del x times x. Once again we can do this, write it as fx, and what extra we wrote? We wrote f del x, right? But this is just 1, so this is f. Okay, so what is f? This thing. So let me put it inside there. This again, del x of fx. Keep it like this, and this is dx and just f. This we know is 0. We proved it earlier. Because once again this will be just, result will be fx, which is this times x, and at x equal to infinity your psi is going to be 0. Psi star is going to be 0. This will come from this term, and then we'll remain with dx and this thing, psi del psi star del x minus del psi del x psi star. We'll do that integration later. Now, what is this? This is some I h cross by 2m here. And this is ddt of this thing. Now, I mean, okay, earlier there was no x, and it was easy. So you said psi and psi star both go to 0 at plus infinity and minus infinity. So this is 0. But now look at this. When you put psi of infinity, there is infinity here. So you have to put x equal to infinity, right? So basically your this times this at minus infinity to plus infinity. So psi of x going to infinity and then multiplied by x going to infinity. That your psi should go to 0 faster. So before x even goes to infinity, psi is already 0 and it will kill the x, right? It will kill the x. It's something like x e to the power minus x. So even if your x is increasing, but it's increasing slowly, while e to the power minus x is dying faster. So even if you go to x tends to infinity, this will never become infinity, this will be 0, because this thing will kill it. And that's why it's important that your psi dies faster than at least 1 over square root of x. And mod psi squared dies at 1 over x. But remember, here we also have del x del psi star. You will see the condition that this must also go faster to 0. I mean, your psi, if it wants to go to 0, then it must have a decreasing slope, right? It cannot be upward. Then how can it go to infinity? And so your del psi del s once again is also going to, 0. So together they will kill the x there, and they will go to 0. So this term actually goes to 0 when you approach infinity. So we are left with only this term. This is your result, more or less. There is this thing in there, IH cross blah blah blah. It was in front. So minus IH cross over 2m, right? We have these two things, and these two things you could apply at least on one of them. On one of them, let's say which one? Let's say this one. You can write once again this as your, so what is this? Del x of psi n psi star, right? Once again, I could just write del x of psi star minus psi del psi star del x. I can write that, right? Just once again, derivative by parts. The dx of some f into g. And if we did that, once again del x of something, when integrated, it will be this, n minus infinity to plus infinity. Once again, psi and psi star both go to 0 at plus infinity minus infinity. This thing will die out, will be remain with this, but then this is this, and there is a minus and minus plus, so in the end it will be just 2 of this thing, so 2 cancels out. Okay, this is where I wanted to reach, and this thing I can write as dx psi ih cross over m del x psi star, right? Can take it inside, del x x on psi star. I can write it like this, d dt of this thing. Now, expectation value of position is, let's say, expectation value of velocity. But in quantum mechanics, we always talk about momentum instead of velocity. So you could take a multiplication by mass and get rid of the m here. This, we say, is an expectation value of momentum. And this thing that is inside, so if you remember now expectation value of anything when we said expectation value of anything, like some f was dx mod psi square f, right? You can write this as dx psi f psi star, right? And if you notice this, then you see that P is dx psi minus ih cross del x psi star. So this thing is like momentum. It is like momentum. It's called not just momentum, it's a momentum operator. And when you have position, then position goes here. This x is position operator. So anything classical mechanically like position, momentum, velocity, kinetic energy, they all become operators in quantum mechanics. Because we don't really measure them the way we do in classical mechanics. Like in classical mechanics, our position is a number that is fixed. We know the trajectory and we know this is the position and this is the momentum. But in quantum mechanics, we don't know. We just know a state. We just know a state on which we perform an experiment on the system and we get a value of position, of momentum or whatever. This mathematically means there is a mathematical operator that you apply and you get a value, we'll come to that, an eigenvalue of the operator. So your position becomes a position operator. Your momentum becomes a momentum operator. But do it yourself, prove this, that ddt of this thing equal to 0. So basically this becomes your minus infinity plus infinity dx del t of mod chi square. So mod chi square is chi star. Prove that to be equal to 0. I did that. You just have to do it again at home. Another thing you have to prove, ddt of this m times ddt is minus infinity to plus infinity dx chi ih cross del x chi star. And let's do a quick problem so that you get a feeling. So suppose we have some potential and you solved the Schrodinger's equation and you got a wave function that looks like this. So suppose you have some system and somebody solved the Schrodinger's equation and gave you a solution that looks like this, and they told you that a, lambda and omega are constants, real and positive numbers, constants. That's given. And they said this is the wave function they got. First question, normalize this. So normalize this means use the condition that total probability is 1. That is the first thing you should always do after solving Schrodinger's equation. So integration infinity to plus infinity dx mod chi square equal to 1. When you do that, mod a square will come out, infinity to plus infinity dx e to the power 2 lambda mod x square of this, right? This is real, so this time this becomes square, and this is e to the power I something, so e to the power minus I into e to the power plus I, this goes away. This must be equal to 1, right? Now look at this function. This is the mod chi square function. So mod chi square is mod a square e to the power minus 2 lambda mod x. Now a is given to be positive and real. There is no point of taking a mod, right? Now if you plotted this, how will it look like? Remember this as a mod of x. So it will look like this. Mod chi square will look like this. And so you know this is a even function. This is an even function. What is the even function? That is just the same this way and just a mirror reflection on this. And if you have an integration over even function from minus infinity to plus infinity, that's just twice 0 to plus infinity. You could just calculate this side and take it double of this, and that will be your total area inside. So you can just write 0 and 2. Now if x varies from 0 to infinity, we are always in the positive side, right? So we can just ignore the mod. It is already 0 to, it's the question when we go to minus x that we not need the mod, right? So just this. And you can easily calculate the integration of this. That will be what? 1 over 2 lambda. 1 over 2 lambda. 2 goes away. Mod a square is just a square because real number. So your a becomes square root of lambda. Now you go back, you put the value of a here. And now what? Your wave function is now normalized. Now always integration of mod chi square will be 1, right? You fixed it by finding out the value of a using that condition. Okay, so mod a square is lambda this. Next question. What is the expectation value of x? Tell me. What should I write here? First probability density and then x. So let's put it here, mod chi square lambda e to the minus 2 lambda mod of x, x. What is this part? Even function minus infinity plus infinity multiplied by an odd function. And that integration is always 0. Integration of an even function times any odd function, and if this is symmetrical, then it's going to be 0. Because look at this, this is even, and x is like this. So your this area and this area will just cancel out. So this is plain 0. Okay? And what is the integration of x squared? Well, that will not be 0. X square. But now once again, minus infinity to plus infinity, this is even, so we can just take 2 and 0 to infinity, and if it is only in the positive direction, we can remove this, and this integration once again, you can use the trick I gave you in thermodynamics. The trick was that, okay, first take lambda outside, it's a constant. That here you have an x square, and here we have x. If we take derivative with respect to lambda of this thing, with respect to lambda, then minus x will come down once. Once again, if you take derivative with respect to lambda, another minus x will come down. So you will have an x square. So I can write this thing as just del square del lambda square, right? And of course there are, these 2 will come out. So 2x extra 4, so just take 1 over 4. Then what will this be? This will be exactly this, right? So 1/4 half here, and now take out the del lambda square outside, and you have a simple integration. You have just integration of e to the minus this thing, and you know the answer. It's 1 over 2 lambda. But now you have to take the derivative, right, with respect to lambda square. So 2 comes here, becomes 4. Derivative of 1 over lambda is 1 over minus lambda square, and so once it gone, so minus here. Once again, this is minus 2 lambda to the minus 3. So this will become 2 by lambda cube, right? So 2, so 1 over 2 lambda square. All expectation of x equal to 0. Expectation of x square equal to this. And somewhere, probably I told you that in your uncertainty principle, we got this del x del p. So this del x, we call this a standard deviation. Standard deviation. Delta x whole square equal to x square expectation minus x expectation square. X expectation is 0, so just this is 1 over 2 lambda square. So this represents the spread in the function. What is the function? The function is mod chi square, which is what? Lambda e to the power minus 2 lambda x. If you plotted this delta x is a measure of how spread out this function is. Is it highly peaked or spread out? That's the measure of the spread. You can also call this sigma. So put a line at exactly where you're, so put a line at plus sigma and minus sigma. How? You have mod chi square equal to lambda e to the minus 2 lambda at x equal to this thing, this maximum spread. I will put the value of x and I get square root of 2 and lambda cancels out. Okay, and take just this equal to 1 because you can normalize this. Okay, so this value is something like 0.24 whatever, I think, and minus will be exactly minus this value. So this is the spread, and then the next question I'll ask is, what is the probability that your particle will lie just outside this range? So it's easy. You have probability density. You have to integrate that in the region that I asked you. Just like the dice throwing. What is the probability that 6 will come? So 6 divided by the total number of possibilities. Like 1, 6 will come, that is 1. So 1 over 6. Here, you have a probability density. I asked you what is the probability that it will be either on this side or this side. So you just have to integrate mod chi square from minus infinity to minus sigma and leave this part, I didn't ask you, plus infinity to plus sigma to infinity, and that is your probability. Or you can just take 1 minus this, because total probability is 1. So 1 minus integration of mod chi square from minus sigma to plus sigma. Okay. And it will turn out to be the same thing, e to the minus square root 2. I'll give you in a proper way the question and try to solve it, but if you can ask me. But this will be more or less like the quantum mechanics. You have an equation. Every time I'll give you a potential and we will solve it for a box, for a harmonic oscillator, for hydrogen atom, all these things. It's never going to be different. Just one Schrodinger equation, this equation. This. I'll give you different V's every time and same the same equation, but we'll get different function because of this different potential. This is all of your quantum mechanics. Basically, there is nothing else.